Hello and welcome to another video tutorial about FreeCAD. In this video tutorial we are going to model this heart-shaped ashtray like it is shown here on the screen. And since we will use the part design workbench to do that, we will have a closer look at the sketcher and the solver. We will also have a closer look at the sketcher workbench and some of its commands. The version of FreeCAD I'm using here is the 0.15 stable release on a Windows 7 64-bit system. Now, when beginning with 3D CAD modeling, a lot of people like to ask as a first question, do I really need to have a fully constrained sketch in order to be able to pad or pocket this sketch or to revolve it? The simple answer is no, you don't need to have a fully constrained sketch to do this. Let's look at an example. We will create a new document. We will set up a sketch on the XY plane. We will use the polyline tool. And we will create a contour. And we will make sure that it is closed. I'll even insert two small circles here, and that's it. I close the sketch. We have an under-constrained sketch with 18 degrees of freedom. So I close the sketch and I pad it. Let's set the length to 20 millimeter. That's okay. And as you can see, FreeCAD did pad the sketch. We didn't have any constraints, except for the obvious ones. The polyline tool with auto constraining set in preferences includes having coincidence constraints on these points. So the only thing validated by FreeCAD before doing a pad or pocket or revolve operation is the contour closed or not? If the contour is not closed, you will receive an error message saying failed to validate broken face. So why do we need constraining then? Well, there are two obvious reasons for that. The first reason is that most parts do have a technical background. That means that, for example, a bolt should fit in a hole, and therefore the diameter of the bolt should be a little bit less than the diameter of the hole. That would be nice in order for the bolt to fulfill its technical function. And to make sure that this is the case, we need constraining. The other obvious reason is that even in our modern times, with computers spread everywhere, the best way to communicate in technical things is to have a good technical drawing showing all necessary views, all necessary dimension, all necessary information. And on this technical drawing, if you apply dimensions to the edges and you want to tell somebody this edge has to be 20 millimeters long, well, you need to model it in 3D with a constraint set to 20 millimeters length. So the real answer to the question is, if we need a fully constrained sketch, we do not necessarily need a fully constrained sketch. But in most cases, if you design a part, you will end up with a more or less fully constrained sketch. What's the story about the sketcher and the solver now? Well, the solver is running constantly in the background and taking into account all manually and automatically set constraints in the sketch. And the solver is trying constantly to find a valid solution. And of course, the solver is reporting back constantly its findings, if everything is okay or if we have a problem. But unfortunately, the solver is not able to tell us what specific constraints we need to be able to fully constrain the sketch. He only can tell us how many constraints we need to be able to solve the sketch. Let's look at an example. Let's open a new document and create a new sketch on the XY plane, and for demonstration purposes we will use a simple line in the sketch. The line has a start point and an end point, and the solver is reporting back under constraint sketch with 4 degrees of freedom. Let's think a little bit. One obvious possibility to constrain the sketch would be to have a vertical dimension and a horizontal dimension as a constraint applied to the start point and the end point of a line. This is called absolute dimensioning. Absolute meaning in regard to the origin. So now we have a fully constrained sketch. We gave an x and a y coordinate to the start point and the end point of the line. Another idea would be to have, for example, horizontal and vertical constraints set up for the start point. Then we will set up an absolute length for the line, and we will set up an angular constraint. And here we go. We are again fully constrained, but we used different constraints than in the first case. Of course, there is a third way of constraining the line. Let's use a second line from the origin to the start point. Let's define this line as construction element. And now let's use polar dimensioning, giving a direction and a length for both lines. So we apply absolute lengths to both lines, and we apply an angular constraint here, and we apply an angle constraint here. And we are again fully constrained, using completely different constraints than in the other two cases. And there are even more possibilities. So as you can see, all the cases here had in common that we had to use 4 constraints to fully constrain the sketch. But since we were able to use different constraints in every case, the solver was only able to tell us, well, we need 4 constraints to fully constrain the sketch. The solver was not able to tell us what specific constraints we should use. That's up to us to decide. Please take into account that also construction geometry has to be fully constrained in order to be reported by the solver as fully constrained. So when using sketches in your 3D model, it is a good idea not to use one single complicated sketch, but to use several less complicated sketches instead. Also, if there is the possibility, try to make use of symmetry or try to use patterns when designing a part in 3D. Now, when constraining a sketch, there is no real golden rule to be followed. But in my opinion, a good workflow would be to first look for the obvious coincidences in the sketch and constrain them. The next thing would be to look for obvious vertical or horizontal lines and make sure that these are all constrained. Then you will perhaps look for tangency, for equality and symmetry. And then you can begin with setting up horizontal and vertical dimensions with radii constraint and angle constraints. And if you have set up all obvious of these constraints, you may be able to have a look at the solver and see if some constraints will remain to be set, and then you have to hunt down all of the constraints if you want to have a fully constrained sketch. Now, as I've said before, FreeCAD will validate the contour, if it is closed or not, before it executes a pad or pocket or revolution operation. So if we use our demonstration object once again and apply to this face a sketch which is not closed, so the contour has here a gap, and we try to apply a pad operation. In this case, FreeCAD will give us no preview of the operation, and if we click on OK, FreeCAD will issue a warning saying failed to validate broken face. This is because the contour is not closed in this case. So we can now switch to a sketcher workbench to validate the sketch, and this is what we will do. So we will switch to a sketcher workbench, we will select our sketch, and we will select from the top menu here, sketch, validate sketch. So now you have access to some tools allowing you to search for missing coincidences by setting up a search tolerance. You can search for invalid constraints, for reversed external geometry, and you can do constraint orientation locking. Remember that when you are in edit mode with your sketch, you also have a list of elements used in the sketch here. You can click on one of the elements. They are highlighted in the 3D view here. So you can search for overlapping lines. Maybe you have a sketch where you have a line on top of another line, and that would lead to also a not closed contour, and FreeCAD would refuse to do a 3D operation with that sketch. The next point is that, for example, let's delete the sketch, then just insert a circle and do a pad operation. And maybe you just have realized that you mapped the sketch to the wrong face. So now you need to remap the sketch to another face. You can do this by using this icon here, or the appropriate command in the sketcher workbench. But since the sketch is already in use by this pad here, it cannot be remapped. Let's select another face for the sketch to be mapped to. Let's select the remap sketch icon and select the sketch 001 to be remapped, and we get a cyclic dependency error. So now we have to delete this pad operation so that only the sketch remains, and now we have to select the new face for the sketch to be mapped to. Again, we have to, as I said, click on the icon here or select from a sketcher workbench, sketch, map sketch to face. We select the sketch 001, click on OK, and now the sketch is mapped to this new face here. So the next point is that let's toggle the visibility of this base object here and toggle the visibility of the sketch here. Okay, so the next point is that there is something special with the pad operation and the revolution operation in the part design workbench. You can either map the sketch to be used for these operations to a face, and when padding, FreeCAD will also automatically fuse the pad to the base solid. And when you choose to map the face, the sketch not to one of the faces of the solids, but to one of the three main planes, you will get an independent solid. So at the moment, if we will have a look at the dependency graph, we will have one object. So maybe you don't want to fuse this, or you want the pad completely reoriented. So this is also doable. If you select the pad 001 in this case and select from the top menu sketch, no, sorry, we have to select the sketch 001, not the pad, since we are in Sketcher workbench, and we have to select now sketch, reorient sketch, and we get a warning that the sketch with a support face cannot be reoriented. Do you want to detach it from the support? If we click on yes, we can now choose a new plane which the sketch should be mapped to. Or if we click on cancel, we just created two independent solids because this pad is now no more fused with the base solid. It is detached from the base solid. Let's have a look at the dependency graph. We have now two objects. This is a trick you can use to model in 3D space. Normally, you would choose one of the main planes, do your pad operations, and then do placement to orient your pad in 3D space, but you can also select an existing face, do your pad operation, and then detach the pad from the base solid, like I have shown here with the Sketcher workbench reorient sketch command. So now that's enough for today with theory. Let's start with finally modeling the heart-shaped ashtray. So let's discard all changes, create a new document, switch to part design workbench, and let's go. So the basis of the heart should be a triangle consisting of construction lines. So the first thing I'm going to do is I'm setting up a sketch on the XY plane. I choose the polyline tool and I will create a triangle here, making sure that this line is horizontal. I will apply equality to these two lines. I will apply an angular constraint of 60 degrees, and I will apply a horizontal dimensional constraint of 55 millimeters to this line here. Now I will select all these three lines and toggle construction mode. So we have now erected the basis of our heart. The next thing is I'm going to basically draw some lines. namely 4 of them. The heart should, at least the outer contour of the heart, is formed out of 4 straight lines and 4 arcs. So now I'm drawing the arcs. I'm making sure that the midpoint of the arc is set on the y-axis, and I'm trying to catch this point and this point. Okay, we repeat the operation here with a midpoint set. Now, with a midpoint set here on the corner of this triangle. You will catch this point, and no, it didn't catch, so we will just set up a coincidence constraint here. Yes, we will try to make this a little bit nicer here. Okay, so the next thing is to set up an arc here with a midpoint on the y-axis. Okay. And we will set up one last arc here. Okay, everything looks nice. So now we will start to set up the tangential constraints. So here we want to have tangency. Let's try to set up a tangency here. Okay, this worked. Very good. So the next thing is we set up a tangency here. Set up tangential constraint here. And here. And here. So everything's set up here. The next thing is that these two lines should be parallel. And these two lines should be parallel as well. Okay, so now we can set up, because of the symmetry of the heart, equality between these two radius elements, and we can try to set up equality between these two radius elements. Okay. So now we have to apply a dimensional constraint of 25 millimeters to this radius, and we will select the lower radius here and apply a dimensional constraint of 3 millimeters. And here we go. We have a fully constrained sketch. We close the sketch. We pad it to a length of 20 millimeters, saying OK, and we just did our first successful operation. Now let's apply a trick we just learned by selecting the basic sketch. Since we want to now create this inner pocket, we will now select Edit, Duplicate Selection to duplicate this sketch here, but this sketch is at the moment mapped to the XY plane. We want to map it to this face, because when we will do a pocket operation. So we choose this top face here, we choose the remap sketch icon, and we want to have sketch 001 remapped. We click on OK, and we will change this radius constraint to be 13 millimeters. And we are set up with a pocket sketch. Of course, we could also try to create edges linked to external geometry and then draw some sort of offset in the sketch and use that for our pocket operation. Okay, we close the sketch and we do a pocket operation. We choose a depth of 15 millimeters. We click on OK. And if we choose isometric view and fit all, our heart will look like this. So let's try this operation again, basically. So we will select the sketch, we will choose Edit, Duplicate Selection, and we will remap the sketch to this top face here, the sketch 002. Okay. And we will change this radius constraint to be 22 millimeters. So now we will draw once again our heart, and we will draw our 4 lines here. When we will choose an arc, to be the midpoint of the arc on the y-axis, and let's catch up these points. So catch this midpoint here, this point here, and this point here. Let's select the y-axis here and catch these 2 points and set up the last arc, set up a midpoint and catch these points here. Okay, so now we are set up with tangential constraint here and here, and let's use these lines. And now set up the tangency here once again, and let's set up one last time a tangential constraint. Okay, now we did set up, as far as I remember, parallel constraint with these 2 lines and parallel constraint with these 2 lines. We did set up an equality with these 2 lines and with these 2 lines equality, and we apply here a radius constraint of 16 millimeters, and we will apply once more here a radius constraint of 3 millimeters. And so we are set up to do our next operation. So let's make sure that the sketch 002 is selected and apply a pad operation with a length of 4 millimeter to get a shape like this. The next thing is we will select this face, and we will also select this face here, and this face here. They are all selected now. And then we will apply a fillet of 1 millimeter to all these faces. Then we will select the inner face and apply a radius of 3 millimeter to get also a fillet here. So now let's create these pockets needed for the cigarette by using 2 times a pocket operation, and the other 2 times we will see what trick we can use there. So let's select this face here and create a sketch. We will use external geometry. We will use the polyline tool to create a line here, a vertical line here. We will use the polyline tool again and start from the same point here, creating a horizontal line, a line sloped a little bit here, and a vertical line here. Then we will create an arc, catching up this endpoint here and this endpoint here. So now we will set up a tangential constraint here, and we will set up a tangential constraint here. We will set up equality here. We will set a horizontal dimensional constraint of 8 millimeters here. We will set up a vertical dimensional constraint of 2 millimeters here. We will set up an angular constraint of 45 degrees here. And we will also set up this angle constraint here to be 45 degrees. So all we have to do now is to set up a horizontal dimensional constraint in regard to the origin of this point of 10 millimeters. And then we have to set up a horizontal dimensional constraint and our vertical one between these 2 points of 8 millimeters, and we are fully constrained. We will do a pocket operation, not only of 5 millimeters. Let's see 2 first. Oh, that looks good. Let's click on OK, and we just did our first pocket. So for the next pocket operation, we will try to reuse this sketch. So we select the sketch 003. We click on Edit, Duplicate Selection. The selected objects have a dependency to unselected objects. Do you want to duplicate? Well, this is the external geometry link, so I don't want to duplicate them. And now I want the sketch here to be remapped to this face. So I'm selecting this face here. I'm selecting remap sketch to face. I'm selecting now sketch 004. Click on OK. I will delete this external geometry here and this 10 millimeter constraint here. I will select all geometry and pull it to the left hand side. Okay. So now again we will use external geometry. We will use this edge here. We will select this point here and this external geometry line here, and we will fix the point on the object. Now we will apply once more the 45 degree angular constraint, and we will apply here also 45 degrees. Now if we select this point and the origin and apply our horizontal dimensional constraint of 10 millimeters once again, we have set up everything. We will apply the pocket operation to first. We click on OK, and here we have both pockets. Okay, so now we want to do these 2 pockets here, and well, it seems like we are a little bit in trouble, because the pocket operation does need a sketch mapped to a planar face, and here we don't have a planar face where we can map a sketch to. So we will use a little trick. Maybe you remember the lesson 2 with a wiffle ball, and where we also had the problem that we wanted to cut off the edges of our cube, and since we couldn't use the pocket operation, since we didn't have a planar face to attach the sketch to, we used the trick that we did a pad operation starting in the middle of 3D space, and then we used the Boolean cut operation to cut the pad from the base solid. This trick we will use here again. Okay, so let's toggle the visibility of this pocket model here. Let's change back to part design workbench, insert a sketch on the YZ and the XZ plane, and we will create this pocket like this. I'm creating some sort of upper head on this pocket to make sure that I get some overlapping of the bodies. If I would just have reused the sketch once more for the pocket, I wouldn't have got overlapping, and that would have resulted in an invalid sketch. So now I'm going to set the tangential constraint here and the tangential constraint here. I'm going to select equality here, and if we set up symmetry here, we will select an overall angle of 90 degrees. We will select here a horizontal vertical dimensional constraint of 2 millimeters. Here we will apply 2 millimeters once more. Here we did constraint to 8 millimeters, and here we constrained 8 millimeters again. And here we will set equality, and we will set these 2 points to be at a vertical distance of 24 millimeters. We will apply OK. We will close the sketch. We will toggle the visibility once more, and we will apply to the sketch a placement, and we will apply an incremental change. We will apply a rotation around the z-axis of minus 30 degrees. Remember that we set in the basic sketch in this triangle an angle of 60 degrees between these 2 legs of the heart. So we click on OK. We do a pad operation. We click on reverse direction, and let's end up with 90 millimeters. OK. And then, as you can see, we now have some overlapping here. We will select the pocket and the pad. We will change back to part workbench, and we will do our Boolean cut operation. And here we are with the pocket done. And now we just have to create the last pocket here. So the last pocket is a no-brainer. We have to just reuse the sketch from this pad here. So I select it and I click on Edit, Duplicate Selection. I will apply a placement, an incremental one, rotation around Z-axis of 60 degrees. I will toggle the visibility. Yes, we did. We were at minus 30 degrees. So now we can see it better. We were at minus 30 degrees, and so I turned 60 degrees in this direction. I will change to Part Design Workbench. And I will do my pad operation. I will click on Reversed. I will set up 90 millimeters again. I will select this cut solid. I will also select the pad. I will change to Part Workbench, do my Boolean cut. And here we are. We have completed our heart-shaped ashtray model. Well, with that operation, we reached the end of today's lesson. I hope I did show some interesting things and that you learned something, and well, have fun with FreeCAD and maybe see you in another video. Bye!